So good morning. My name is Frances Perry.
And I'm Tyler Akidau.
And we are both engineers at Google and also committers on the Apache Beam project.
And we're here today to talk to you about stream processing and more specifically this unified model for both stream processing and batch processing. But this unified model within Apache Beam that we've developed over a number of years that we think really makes it relatively easy to think about stream processing and build stream processing applications that are robust and able to give you the kinds of results that you want.
All right, so we're going to start today by talking about data shapes. What kind of data are we interested in processing?
After that, we're going to move on to the second section where we're going to look at the 4 questions that underlie this model: what, where, when, and how.
Then we want to explain to you why those are the right questions for solving these types of problems and how they make it very intuitive to reason about a very complex set of use cases.
And then at the end, we're going to wrap it all up by making it a little more concrete and looking specifically at what this incubating Apache Beam project is.
All right, so let's get started with data shapes. So throughout this talk, we're going to be using a running example. And in this example, we're a mobile gaming company, and we've just launched a new mobile game for users across the world. So we've got users all over the globe, and they're frantically doing some sort of mind-numbing task on their mobile phones.
Crushing candy, killing orcs, whatever the kids are doing these days.
Yeah, we're not kids. Every time they do this, they're earning points for their team. And we'd like to analyze those logs and figure out what's going on, how our game's being used.
And so as we do this, we're generating some user events, some data. So each of the colored squares in here represents some score for a team or something like that. And as we start out, our app is new, so our data is relatively small, and it looks something like this maybe.
Now our game gets a little more popular, so our data set gets bigger.
And then it gets really, really popular, and our data starts to get so big that we have to start introducing some sort of structure to it to keep it manageable. So maybe we start siloing it into these daily groups of data so that we can deal with the fact that our popularity has massively scaled up our data size.
But really, this kind of organized, repeated structure is just a cheap way to represent an infinite stream of data. Right? Once our game launches and users start addictively playing our awesome game, they're never going to stop, and those events will just keep streaming into our system for processing.
But given that we've got this massive scale data, we're doing this all on top of distributed systems. And as you know, distributed systems being distributed can introduce ambiguities.
And fun. So let's look at some points that were scored right about 8 o'clock in the morning to understand what distributed systems are going to cause here. So this red score happened right around 8 a.m. and arrived in our system for processing almost immediately.
And the second one here, this yellow one, also happened at 8 a.m., arrived a little bit later, 8:20, 8:30, something like that. Maybe there was network congestion, who knows, some blip in the distributed systems caused it to show up later.
And over here, we've got this green score. This happened at 8 a.m. The user crushed the candy or whatever they were doing, but it didn't make it to our system until closer to 2:30 in the afternoon for processing. So perhaps this was a score where a user was online or playing our game on their phone in seat 26B on a transatlantic flight with no elbow room, right, in airplane mode. And it wasn't until that plane landed and that user reconnected to a network that their phone was able to send that event to our system for processing.
So now we've got this unordered, infinite data set. How do we process it?
So some kinds of processing are actually pretty simple. So element-wise processing is anything that looks at an individual element and can process it by itself. So this would be something like parsing, translating, filtering, any of those types of things.
But most other types of things you would want to do involve some sort of aggregation of multiple events, counting, joining, things like that. And so you have to be able to combine these multiple events together.
And whenever you're doing this kind of aggregation, you need some way to take that infinite stream of data and chop it up into finite chunks so that you can actually complete your aggregation and emit a result.
And the simplest way to do this is to just say, as my data arrive, I'm going to kind of chop it up into these fixed intervals that are just contain whatever data arrives in that hour of time or whatever it is when it shows up, and we'll process it there.
But the drawback of this, right, is if you remember that element, that green score that shows up about 2:30, we're now going to process it with other scores from the 2 to 3 o'clock window. And that means it's being processed out of context. Now, depending on our algorithm, this may or may not be a problem, but it could lead to incorrect results.
And so what we really want to be able to do is to process events in the context that they actually occurred. And so that's sort of what this diagram is trying to show. As inputs arrive, we actually want to shuffle them into the right space to process them within that context when they occurred.
So if you look at this red element here, it arrived in the system just after 12:30. Maybe it also happened pretty much immediately then. So we'll keep it in that 12 to 1 o'clock window.
The green one, on the other hand, arrived around the same time as the red one, but it actually happened much, much earlier. So if we just processed it in that 12 to 1 o'clock window when it arrived, that would have been the wrong set of, the wrong context for that event. So what we actually want to do is shuffle it back into that 11 to 12 window and process it with all the other events that happened in that period.
So conceptually, this kind of reordering makes sense. But to do this in practice, we're going to have to formalize that difference between event time and processing time.
So we're going to be seeing a bunch of graphs that look kind of like this throughout the talk. The basic format is you've got these two axes of time. So you've got event time. So these are the times that events actually happen, and it's on the bottom axis, the x-axis in blue. Then you've got processing time, which is the time that the system itself observes the events when they come into the system. So when are they actually processed? And that's on the y-axis in green.
Now, if distributed systems weren't so gosh darn distributed and everything just arrived in our system immediately, we'd see everything arrive on that ideal line, where it's event time and processing time were indistinguishable.
But reality looks a little bit more like this red squiggly line, where processing time is slightly delayed off of event time.
And what you'll see is that delay is variable. It changes over time depending on the behaviors of that distributed system. And we call this distance the skew.
And so we need to track this in order to reason about completeness and correctness within the system. So within the beam model, we refer to this red line as the watermark. And it's a statement that no event times earlier than this point are expected to appear in the future.
Now this watermark can be either perfect or heuristic. A perfect watermark is possible in a few rare situations where we have perfect knowledge of our input data.
So an example of that might be if you have sequential log files like Kafka that Neha was talking about. If you know a static set of log files ahead of time, and you know that within a given log file, event times are continually increasing, then you actually have perfect knowledge of all of these events, and you can construct a perfect watermark.
But our more common in a distributed system is that we have to use a heuristic watermark. The system has to make its best guess of when all the events for a given time have arrived and the data is complete.
So this is especially true in the case of mobile events. We talked about mobile devices go online and offline all the time. They may stay offline for large periods of time, and there's just no way for the system to know about this. And so given that, there's just no way to provide a completely accurate prediction about when you're going to see all of the events for a given point in time.
And when we start dealing with the watermark, we have to deal with cases where it's a little too slow or too fast. So if it's too slow, and the watermark is basically holding up our results, this is going to introduce unnecessary latency into the system. We're going to have to wait a really long time because maybe there's just one more late element coming, even though we have the bulk of our data, and we can't give you any result if we're holding on waiting for that flight to land.
And then the other problem is that they can be too fast. When you're using these heuristic watermarks, doing your best to estimate completeness, it's still an estimate. And when that estimate is wrong, you may end up getting events that show up late, and you've got to figure out, what am I going to do with these? Am I going to throw them away? Am I going to incorporate them somehow?
So this is the environment we're in, these types of infinite, out-of-order data sets. And we'd like to do our data processing within this environment. So we think this can actually be pretty intuitive if we break it down into these 4 questions.
So the 4 questions are, what are you computing? So this is essentially, what transformations do you have in your system? Are you, summing integers, counting up total scores? Are you building histograms? Are you computing machine learning models? This is essentially the question that folks have traditionally answered using classic batch processing. What is it that I'm actually calculating?
Once you've figured that out, you want to think about how the event time is going to affect results. So does the time each event originally occurred affect how you'd like to create the results? Are you aggregating results based on event time fixed windows or sliding windows or bursts of user activity?
And the third question, independent from the event time, is when in processing time does the system actually materialize these results? Do you want exactly one answer for a given window when you think that all the input for that is complete? Or do you want to see speculative results for things build up over time? And then what do you do if there are late data in the system? Do you want to just throw those late data away, or do you want to incorporate it into the results somehow? Just when as the system is processing things, do you actually create results?
And then finally, how do refinements relate? So if I choose to emit multiple results over time as more data arrives in the system and my results become more complete, Do I want those different results to build on each other, or do I want them to be independent and distinct?
So now we're going to dive into each question in a little more detail, and we're going to do it over the course of an example as we build a pipeline.
Right. So the first thing we have to figure out is what we're actually computing. So we talked briefly earlier about these different types of transformations, right? We have those element-wise transformations, where you're just looking at a single element in isolation. And you can think of this very much like the map function in MapReduce. It's very easy to parallelize because of that independent computation, right? So you can farm it out over as many machines as you like.
So then we have aggregations. These are counts, these are joins, things like that. Any time that you are combining multiple elements together. And this tends to correspond more towards the reduced portion of a MapReduce.
Now, there's also a set of operations that are really just made up of other operations. So things like joins, counts, a lot of these are basically just built up of more primitive operations, but it's useful to roll them up into a composite operation and not have to worry about the details of how it's actually implemented.
All right, so now let's actually see a code snippet for our gaming example.
So the code snippets in this talk are pseudo-Java. They almost compile, but we wanted them to fit on a slide, so we sort of elided some of the details.
And so what we have here are essentially three different statements. To begin with, we're going to read a collection of raw log lines from some I/O source and store that in. So in Beam, a P collection is essentially, you can think of a representation of a potentially massive scale collection. In this case, it's a bunch of strings. So we're just saying we're going to read from some I/O source this raw set of log strings.
So then what we'd like to do is do an element-wise transformation to take each of those log lines and parse it into a more structured format. So here we're going to take each log line and create a key value pair, extracting the team and the number of points scored for that team.
And then once we have these individual scores that have been tallied for given teams, we're going to take those and we're going to apply this composite transformation, sum integers by key, and we're going to sum those up. So this is going to give us per team totals of scores.
All right, so now let's look at some sample data so we can start seeing how this executes. Again, same graph as before. So we've got event time in blue on the x-axis and the green axis showing processing time. And that ideal line is shown here where everything would arrive if there wasn't a delay in the system.
And then all these circles with numbers in them are essentially individual scores for the team. And we're going to go through and sum these up. And you'll notice, looking at a couple of these, like the three here that we've highlighted, this event occurred and then was also observed by the pipeline relatively quickly. So it exists relatively close to that ideal dash line.
The score of 9, however, is more like 7 minutes delayed, right? It happened just after 12:01, arrives in the system for processing just after 12:08. So maybe this user was playing our game in an elevator or a subway, somewhere with a temporary lack of network connectivity.
And this graph isn't even large enough to start to show the types of delays that you would get with folks playing the game on a transatlantic flight or something like that.
So now we're going to start animating this to show how processing time, show how things execute. So what you see here is time is progressing as this thick white line as the computation is going. We're summing up the scores we encounter into that intermediate state that's tracking the white line.
And remember, this is still just classic batch processing here. And so the system continues to build up this sum until it's seen all of the inputs. And once it's finally seen all the inputs, then it generates the final output answer, which is when the rectangle turns blue.
And here you'll notice we're covering all of event time with one result. So we're not really paying attention to when the events happened. We're just summing them up. So this is basically equivalent to traditional batch-style processing.
So let's now see what happens when we go and start playing with the other questions.
So the first thing we're going to look at is windowing. And this is the question that talks about event time. So windowing is going to let us create independent results for finite slices of event time.
And so on this slide, we have 3 examples of relatively common patterns of windowing. So the first one is fixed windows. This is just essentially saying we're going to take time, and we're going to slice it up into these fixed divisions that you know ahead of time. They apply across all the keys, hourly windows, daily windows, those kinds of things.
The sliding window says something like, every hour, give me the last 24 hours worth of data. So the cool thing about sliding windows is they actually overlap. So a single element can conceptually be in multiple overlapping windows and and contribute to multiple results.
And then the last example we have here is sessions. Sessions are really interesting for a couple of reasons. One is that they're based off of the data themselves. So you don't know a priori what a session for any given user is going to be. And then the other interesting thing is that they're unaligned. They're not the same for each given user in the system because I didn't define up front. A session is essentially something that tries to capture a burst of activity or a sequence of events that are somehow related, typically in time. And so when you're talking about like user interaction over a website, naturally different users are going to have different bursts of activity and bursts of interaction. And so sessions themselves inherently capture information that is part of the data itself. It's not just something that you assign ahead of time. So that makes them both very powerful but also very complicated to build yourself.
Now, using windowing is very common when you're processing these unbounded infinite data sets in stream processing. But it's actually also something we've done for a very long time in traditional batch processing. However, in that situation, we usually use something like a composite key and don't tend to think of it as windowing, but the same kind of computation applies.
So let's now go back to the code, and we're going to start adding in these answers to these other questions. So we've elided the first two steps of the code because those aren't going to change for the rest of the pipeline. So we're just looking at that last step where we were doing that integer summation. And so what we have here then highlighted in black is the code that we've added. And so all we're saying is once we have our input that's been parsed into these team score key value pairs, we're going to go ahead and window it into fixed windows of 2 minutes, and then we'll go ahead and apply our summation transformation. So
now if you look, you'll see that we're computing 4 independent results, each for a 2-minute slice of event time.
And as before, this is still batch processing, so we wait until we've seen all of the inputs before we provide any results. And that's fine for bounded data sets, but that's obviously not going to be practical for unbounded data sets because we can't wait until the end. There is no end.
So what we want to do there is start decreasing the latency for individual results. And to do that, we have to look at the third question of processing time.
So to answer this question of when in processing time, we're going to want to start using a tool called triggers. So triggers are a way for you to dictate when results within your pipeline are going to be emitted.
Now, triggers are often going to be relative to the watermark, which again is that system's best guess of data completeness and event time progress.
So again, let's go back to our code, and we're going to insert a triggering statement here that simply says I want to trigger each of these 2-minute fixed windows when the watermark passes the end of it. So that when the watermark reaches the end of that window, that's basically a statement from the system saying we believe that all of the input that you're ever going to see that is relevant to this window has been consumed. And so it's safe to go ahead and give what we think is a complete answer.
So now let's look at how things execute with this triggering. So the graph here shows a perfect watermark. This is what would happen if the system knew exactly when the data for a given event time was complete.
And so the watermark is represented here by that green dash line, and you can see it essentially follows the curve of the data as they arrive. And once the dash line passes the end of a window, then the system is free to materialize the result. So we first get a result for the first window, and then very quickly afterwards, as the watermark traverses to the right, we get outputs for the other 2 windows.
And here you can see one of the drawbacks that comes from waiting for late data, right? That first window, we're waiting a long time after that window is passed just for that one late element 9, right? So here we only have 2 elements, but you could imagine a situation where the vast bulk of our data has arrived, but we're just waiting on 1 or 2 late elements. So we're introducing this unnecessary latency into our system.
So let's go ahead and now look at the second graph on the right. So this is same input data, but this time we're using a heuristic watermark. That's with the solid green line. And you can see that being a heuristic, it's less conservative than the perfect watermark on the left. But the big omission here is that the watermark doesn't take into account that value of 9 that in this case showed up late.
So here we've got 2 problems, right? Sometimes we're waiting too long to get any results out of the system, and sometimes we're moving on too quickly, leaving elements abandoned behind. So we can address both of these problems with using a more advanced trigger.
So back to the code again. What we've done now is we've added 2 modifications to our trigger. We basically said, well, we want to solve the too slow problem. We'd like to have early speculative results over time. So we add this with early firings clause that just says, every minute of processing time, if you have anything new to report to me, go ahead and give me an update. That way I'm going to get continuous updates to my results over time.
We've also added another clause to ask for late firings. So here, if we expect our elements to be late elements to be relatively rare, we might decide that every time we see a late element, we'd like to go ahead and update our results.
So if we go back to the animations now and look at this, you can see it looks very similar to what we had before. But for certain windows, as time progresses, we're going to give early updates anytime that we've had updates or that we've had data that's worth reporting about for more than a minute. And those are all annotated as early. Once the watermark passes the end of the window, if there's something new to report about, again, we'll give an on-time firing. And then on the graph on the right, where that 9 shows up late, you'll see we also give immediately that late firing, saying, we'd given you an on-time firing. We thought the value of this window was 5, but then this 9 showed up, and we need to give you a new update. We need to tell you it's actually 14.
But every time we choose to give you multiple updates, we have to decide how they're going to relate. So if you look at the last window, we have a speculative firing with 3, and then we get some more elements in with a total of 9 right before the watermark. Now we can choose what we'd like that final result to be. In this case, we've accumulated, so we're giving a final score of 12 and including the results from that earlier speculative result. But that behavior is actually configurable. And that brings us to the final question in the model.
So this last question, how do these refinements relate? In order to walk you through the different options we have here, we're going to have a little example here on the table. So the idea with this table is we're going to imagine that we're getting 4 elements in that we're going to process. So that's what the 3, the 5, the 1, and the 2 are. And as they arrive, we're going to have 3 trigger firings. We're going to have a single early speculative firing. We're going to have a single on-time watermark firing, and then we're going to have a single late firing. And we're going to see what the actual materialized outputs for those firings are depending on which accumulation mode we've chosen.
So the first mode is discarding mode. And here, you only include values that have come in since the previous firing. So you can see our first firing includes that 3, but our second firing only includes the new elements that have come in.
And then if you look at the bottom, then we have 2 rows down there, last observed and total observed. So the last observed tells you what is the last thing I saw from this pipeline. And it gave us a value of 2, which obviously is not the correct total sum. So this is sort of the shortcoming of discarding mode. But if you're sending these outputs into a system downstream that is also itself doing summations, then you get exactly what you want. That downstream system is going to take these individual disjoint outputs and sum them up to give you the right total. So you get that 11 in that case.
Now another option is accumulating mode, which is what we had on the previous slide. So here, the total running sum is emitted every time we do a firing. But you can see now the last observed value is correct, but however, the total observed may overcount. So again, depending on what you're doing with this data downstream, if that system isn't able to handle these multiple firings, you could end up with incorrect results.
And then the last example we have is accumulating or retracting mode. So in this case, we're still doing the accumulation that we were doing before. But in addition, every time we have a refinement of a previous result, we not only give you the new updated result, but we also give you a retraction saying, hey, previously we'd said, like for the second firing, we'll give you the 9, this is the new value, but also previously we'd said that the result was 3. Well, we're going to say, take that 3 back. Here's sort of a negative 3.
All right, so let's go ahead and change our running example to use accumulating and retracting mode. So again, just a small code tweak.
And then back to the animation here, you can see this looks a lot like what we had before, where as results evolve over time, we give these speculative updates and new values. But you'll notice each time we provide a refinement to a value, we also, in addition to giving the new value, we give this retraction that tells you, previously we'd said, a certain value, now we would take that away. And this is really important in like, if you have a system that's performing multiple aggregations in a row, that early firing and then the later on-time firing or late firing, if you rekey your data downstream, those might end up going to different places. And you can't just assume that you can overwrite the previous value with a new value. You may need to actually have a retraction for the first value sent to one place and then this new value sent to another place. So being able to have both of these sides of the coin sent throughout the pipeline or sent downstream is really important for having correctness everywhere.
So those are the 4 questions, the what, where, when, and how of data processing, right? And we think that's a really intuitive framework for understanding these complex, infinite out-of-order data sets and how to process them. So now we'd like to try to convince you why this framework is so powerful.
So we have here five reasons why we think this model is really powerful. We'll just kind of walk through them real quick. The first one is correctness.
Now this isn't something we've historically thought we could get from streaming systems. Right, so this is a pretty big deal.
Yeah, so many of you may be aware of sort of the history of streaming systems and how there's for a long time been this baggage of streaming systems not being able to compute correct results, having inherent systematic things built into them that make it difficult to actually get correctness. But if you build your systems properly and you also approach the problems properly, that's not actually true. And so we'll look at an example here that's going to highlight this a bit.
So again, remember that the processing time, the time things arrived in the system, is really at the whim of the distributed system that you're dealing with. So depending on the day, depending on the time, the wind direction, right, your results might arrive in a slightly different order.
And so what we have here, we've got our 10 events, and the white version is what we've been seeing all along, right? But if things had happened differently, or if we're reprocessing data and the stuff, everything percolates through the system slightly differently, they might have arrived in the order that you see in the purple version. The thing to really note here is that the X positions for all of these events is the same here. The events occurred once, right? They always occurred at the same point in time. It's just when we actually observe them with the system may differ depending on how the system sees the events or when we do the processing, things like that.
So let's look at the impact of those changes, right? Processing time is going to look like this.
So these graphs deserve a bit of explanation. So what we're doing here is trying to explain to you what it looks like when you use processing time to compute windowed aggregates of your inputs. So in the light gray, you can see the orderings of when these events actually happen. But when you're doing windowing within processing time, what's really effectively happening is as an event shows up, you're throwing away whatever event time that event actually had and saying, you know what, actually I'm going to just pretend like the time that this event arrived in the system is its event time. So that's why all of these events are effectively being shifted over onto that ideal. But the result of that, you can see, is that depending on which order they show up in, you actually get different results.
So here, the undefined behavior of your distributed system is actually leaking through and affecting your results.
And what we'd really like, what would be ideal, is for regardless of the ordering of when things arrive, we end up with the same answers.
So let's look at what happens if we aggregate based on event time. Right? So here, you'll see that we do have different intermediate results. Those speculative firings, the on-time, the late firings, are giving us different results because the data is arriving in a different order. However, the final result for each of these windows is identical, regardless of the input ordering.
All right, so next up, power. So what we're really getting at here is that with the Beam model, you can do really powerful things without a whole lot of effort. So as you may recall earlier when we were talking about session windows, I'd mentioned how those are a really powerful concept that allow you to really learn very interesting things about your user data, but they're also really complicated to implement. And so let's talk quickly about what we mean by sessions.
So what we have here is we've looked to identify the points that we have for a given user, and we're dividing it up into two bursts of user activity. So you can see the user was sort of playing for a while here, took a 2-minute break, got distracted by something, then came back and played our game some more. So there are many cases where we'd like to treat these as two different sessions of user activity and process the elements based on the session in which they arrived.
And so doing this yourself in code is actually quite a lot of code work. There's blog posts out there that kind of explain how to do it on various systems, and it's non-trivial. But the way that you can do it within a system like Beam, where we've carefully abstracted apart these different questions that you're answering and allow you to swap in and out new answers to the questions, means that you just walk in here and you throw in this one-line change of saying, we used to have fixed windows in here. Well, now we're just going to say, we actually want a window by sessions. Everything else stays the same.
And now you can see that as we're going, we're really building up these sessions over time. As elements come in close conjunction with each other, we're able to treat them as a single session. So you can see we're starting to build up sessions. We start merging things as we process new elements. And what you see here is that late element of 9 is really key in getting the correct results here, because we only have 2 sessions. But until we see that late element, it looks like we have 3 sessions.
All right, so next, composability. So we've shown you a bunch of examples where you kind of ask the 4 questions and answer them, but you actually can ask these questions multiple times, and that just extends further the amount of power you have with the system.
So what we have here is some code that's calculating the length of a user session. So we're windowing into sessions, triggering at the watermark, and then we're just calculating the length of each session. We're not trying to sum the scores right now, just figure out how long that burst of user activity was.
And so this length of user activity is a reasonable proxy for user engagement. So this is a metric that's commonly used just to see how long are users playing our game, crushing candy, killing orcs.
So remember, these graphs we've been showing you are per key. So Tyler and I, as two users playing the game, each have our own graph here, right? Because we each have distinct sessions, our own patterns of playing this game.
And this, oh, that's fine. So once we've calculated session lengths then, the next thing we're going to do is go ask the questions again. And this time we're going to say, okay, well, we've computed individual session lengths for all of our users. But in order to really infer something interesting about our system, let's go and we're going to window those sessions into fixed windows so we can sort of group together sessions within a given time period. And then over that time period, we're going to compute a global average. So we're going to say, within this fixed window of an hour or 2 minutes or whatever, what is the average session length? And this will give us, over time, a view of user engagement as it evolves, as our system changes.
So you can see here, we could use this for something like tracking new rollouts. So we just pushed a new version of our game to prod, and it's rolling out, and our users are starting to engage with it. If over time, then, we see a sudden increase in the average length of a user session, then that new game, that new feature that we've rolled out must be really engaging, right? It's causing users to not get distracted and to focus on our game for a longer time.
So now to move on to the last two. So flexibility. The system gives you a lot of power to choose exactly what the shape of your output looks like. We walked you through so far 6 different examples.
So here we've covered everything from your classic batch-style processing all the way up through some very complex stream processing.
And what's more, moving on to the last point, modularity, we've done this with really quite minimal code changes. Very small changes that are still maintainable and leave your code readable and allow it to evolve still over time as needs change.
So here, the core algorithm that we're running was just integer summation, right? It's very simple, but this same kind of modularity applies to much more complex algorithms. So the bulk of your code, the bulk of what you're doing is your really complex user logic. That will all stay the same as you tweak these other 3 questions.
And so there you go, 5 reasons that we think the 4 questions are awesome.
All right, so we've got these 4 questions. But that's no fun unless we actually have a framework that's concrete, right, where you can get your hands dirty and start playing with them. So that brings us to Apache Beam.
So to begin with, we'll look and see where this model and then eventually Apache Beam came from our perspective. So for us, it all began back with MapReduce. So the original MapReduce paper was published back in 2004. And it fundamentally changed the way that we think about massive scale distributed data processing.
Now inside Google, we kept working after MapReduce, and it evolved into a number of new systems. And as we were building these systems and using them internally, we continued to publish papers. So we were sort of writing these papers, lobbing them over the wall, but really just focused on our own internal needs.
Externally then, as you're all well aware, an open source ecosystem flourished around initially these ideas around MapReduce, but then adding in all sorts of other innovations and other ideas and really turned into this massive ecosystem of open source software that you all utilize today.
So in 2014, Google announced Google Cloud Dataflow, which was part of our cloud platform, and it was a product and a fully managed service based on these years of internal data processing. Now, there were really 2 parts to Cloud Dataflow. There was the SDK and the programming model, originally called the Dataflow model, which is what we've been discussing in this talk, that you use for constructing your pipelines, and then a no-knobs managed service for executing them.
But we didn't want to stop there. There were 2 things, really. We wanted to share this model more broadly, both because it's awesome, but also because we realized, looking at the success of open source ecosystem, that users really benefit from having this larger ecosystem and having portability across systems and the ability to choose amongst these other open systems.
So Google, along with a number of our partners, went ahead and donated this programming model and SDKs to the Apache Software Foundation as the incubating project Apache Beam. So today, Apache Beam includes essentially the following 3 things. Firstly, it is this conceptual beam model that we've been talking about, the underpinnings of which are this what, where, when, how model of thinking about data processing. Then we have what we hope becomes a very large set of SDKs that let you actually express the concepts in this model. So we're starting with the Java SDK, which came almost directly from Google's original Dataflow SDK, modulo a very large package rename. And we're also working on a Python SDK, which is on a feature branch in the Apache Beam repository. And then lastly, the part that actually makes this portability thing happen is that we have runners for a number of existing distributed processing backends. So we have runners for Apache Flink, Apache Spark, and Google Cloud Dataflow. There's a direct runner for local development and testing.
And then, as part of community involvement and actually building an ecosystem around this within the greater open source community, we now have 2 other runners in development contributed by folks from these 2 communities of Apache Gear Pump and Apache Apex. With Apex is both of those are currently in feature branches. Has Apex moved?
Apex is going to merge in any day now.
Apex is imminently moving into the main feature branch, or the main branch of Beam.
Because our goal with Apache Beam is really to support 3 distinct user communities, right? The first is end users. These are folks who have data, they have business needs, they'd like to write their logic and process their data, and they want to do this in the environment that they're familiar with, the languages their company has already chosen, the distributed processing backends they're already using, either on-premise or in the cloud.
The second is SDK writers. So these are the folks that want to make the Beam concepts, the Beam model, available to folks that want to develop in new languages. So you want to have a Go SDK, or you want to have a Visual Basic SDK. Go for it.
And then finally, we have the runner communities. And these are the folks who are part of and deeply involved in a distributed processing backend, be it Flink, Spark, Apex, whatever. And what they'd like to do is add support for Beam pipelines so that they can take the concepts and the programs written against them and go ahead and execute them on their backend.
So having a vision and reaching it, though, are 2 very different things. So
Beam entered incubation in very early February of this year, and then very quickly after, we dumped 48,000 lines of initial code into the Apache repository.
So what followed then was a period of chaos, de-Googlification, generalization, a lot of work around making this into an actual system that can be worked on by a large community outside of Google in a very general way.
So we've been getting into the cadence of doing incubating releases. We've grown some new committers in the community working on things like Gear Pump and Apex. You've seen us do a lot of API changes as we try to stabilize the APIs between components and get ready. But we're really getting to the point where this promise of portability is true, where you can take a single Beam pipeline and smoothly run it across any of these runners.
And then once you get to that point, and you have folks actually interested in picking a runner to run on, then you now have this other problem you have to address of how do they understand what different runners can do?
So that brings us to the capability matrix. So what we're trying to do with the Beam model is really generalize the semantics of this style of data processing, right? We're trying to come up with the best, most intuitive way for you to represent your computations.
And so what we've done is we've categorized features within the model, and these are broken out into categories that match the what, where, when, how questions. The colors sort of match the colors we've had throughout here. And for each of the features then, each of the columns shows you, for the given runners that we have, what level of support we have. And you can see in general, most folks within the industry are moving towards supporting everything within the Beam model. One thing worth calling out here is that the Spark column is missing a few things there. That's primarily because this is built on top of Spark 1X. As Spark 2.0 matures, which is bringing with it a lot of the stuff within the Beam model into Spark itself, we expect this to change. And also the folks that are working hard on our Spark runner are also working at building in support for this within Beam on top of Spark 1X. So you'll actually be able to do things with Beam that you otherwise would have to do manually and requiring much more effort on top of Spark 1X once they manage to flesh out all of those columns.
All right. So I think we've got really different takeaways here for different folks. If you're just getting started with stream processing and you're still trying to figure out the concepts and how you can think about these style things, I really encourage you to go check out Tyler's blog posts on Streaming 101 and 102. They're basically a much longer, more detailed, and slightly snarkier version of this talk, but they're a lot of fun.
And then if you want to learn more about Beam, come to our website. There's lots of information there, both if you're interested as a user, as an SDK writer, or as a runner builder. And if you'd like to join the community, there's our mailing list, and we would love to have you come and help us build this sort of future vision of data processing.
The way we've seen the community grow over the last few months has just been amazing. What happens when you take something that was designed in a very hermetic environment and you generalize it and you bring in the power of new ideas? So we're really excited about the Beam community and its growth. All right, so we'd love to take questions either here or offline. We'll be around all day. So.
Thank you very much.